Hello guys, today we're going to make another calculus video. We're going to talk about concavity and inflection points. And these both have to do with the second derivative, which we talked about a little bit on the last video. And we're going to talk about how we can use this to figure out some things about our graph, and also use our graph to figure out some things about our function. So what is concavity? Well, concavity is an aspect of a function at a certain point. So at a certain point, a function can be concave up, or it can be concave down. Concave up means that the second derivative is positive, and concave down means that the second derivative is negative. What does this really mean? This means, first of all, that at maximum points, we will have concave down, as we talked about in our last video, and in minimum points, we'll have concave up. Well, let's look at a picture here. So if we have some function like this, as you can see, the function is increasing, but the rate at which is increasing is going down. And at this point right here, it starts decreasing. So for all of this, as you can see, it's starting to kind of curve downwards, because at first it's going almost straight up and it starts to curve downwards, and then it keeps going down. So this means that it's concave down, but at a certain point, maybe it'll start switching. You see here, it started to switch and it started becoming concave up. And so we can actually look at our graph of a function and try to determine what domains are concave up and concave down. So that brings us to inflection points. Now, an inflection point is a point where the second derivative is 0. And it's also a point where the second derivative goes from being negative to positive, or goes from being positive to negative. So if, for example, it goes from negative and then it goes to 0 and then it goes back to negative, that's not an inflection. So we're going to look at these two functions. So as you can see here on this function on the left, it's going concave down, concave down, concave down, because as you can see, it's starting to curve downward, and although it's increasing, the rate at which it's increasing is actually decreasing. Then when we reach x equals 0, it starts to increase again. So we can infer that x equals 0 is an inflection point where it goes from being concave down to concave up. Same thing here with y equals sine of x. We have concave up because the function is curving upwards. Then when we hit 0, we're going to have concave down because it starts to curve back down. So let's look at some steps that we can use to solve some problems. So if we have a graph, the first thing we're going to do is we're just going to try and look at the graph, and we're going to try to determine just at a certain point whether it's convex up or down. And then we're going to try to then find the point where it switches to being the other one. So if it's being convex up or down, we're just going to look for inflection points. And then once we found all our inflection points on the graph, we can just state our answer. But algebraically, it's going to be a little bit different. So first thing we're going to do is we're going to solve for f double prime of x. And the second thing we're going to do is we're going to solve for f double prime of x equals 0. And so this is going to give us, hopefully, our inflection points. The last thing we're going to do is we're going to draw a number line. So let's say f double prime of a and f double prime of b are both equal to 0. We're going to put our points on our graph, and we're going to highlight all the domains that are going to be concave up and concave down. So for example, for any point between b and a, since we know that they're only 0 at these points, we can say that they're all either going to be concave up or all concave down. So we can just plug in any point here, and if we find out it's concave up, we'll do this. And then we'll plug in any point greater than a, and if we find out it's concave down, we'll do that. And we'll just do that for every domain. So let's get started on a few examples. So here's a visual example. We're told to find all of the inflection points in the graph and state all the domains in which the function is concave up and down. So first thing we're going to do is we're just going to look for our inflection points. So I'm just going to follow the graph here. Going from the left here, it appears to be concave down because it's curving downwards. But clearly over here, it's concave up as it reaches this minimum point. So somewhere in the middle here, around here, is going to be our inflection point. So I'm just going to say this is 0, 1, 2. I'm just going to say that x equals 2 since we're told to estimate. It doesn't need to be that accurate. So we're going to say x equals 2 is our inflection point. And then now we need to list all the domains in which a function is concave up or down. So the function is concave up, not in this area, nothing to the left of our inflection point because this is all concave down. It's everything to the right. So we're going to start at 2 and we're going to go to infinity. And that's where we're concave up. When we're stating concavity, we're always going to use these open brackets because usually this left bound or the right bound is going to be an inflection point, and at inflection point the second derivative is equal to 0, it's not positive or negative, so it's neither concave up nor concave down. For concave down, we're just going to have every point to the left here, so that's negative infinity to 2. That's our answer. Now here's another question. This looks a little bit more difficult. We're doing the same thing here. So I'm just going to start from the left. As you can see, we're concave up because the function is curving upwards. But around here, we start to be concave down as we reach this maximum point. And then here again, we start going back up. So this is going to be concave up again. So I'm going to say that this is x equals -1 and x equals +1. And that's going to be our inflection points. So for concave up, as we said, it's going to be this area and this area. So concave up is negative infinity to -1, then union +1 to infinity. And for concave down, it's just going to be everything in between here, -1 to 1. And that's our answer. All right, move on to the next question. Okay, now we're going to do this using math. Calculate all inflection points in the function and state all domains in which the function is concave up or down. So first we're going to find f double prime of x. So f prime of x equals 3x squared plus 4x minus 1. F double prime of x equals 6x plus 4. So we're going to set this equal to 0, and we find that x equals -2/3. I'm just going to tell you real quick that every cubic is only going to have one inflection point. So that's something that you can generally look out for to see if you did something wrong. Since this is only a cubic equation, it only has one inflection point. So now let's draw our number line. So we want to figure out if anything less than -2/3 is concave up or concave down. So I'm going to plug in -1, which is less than -2/3. And this is going to be -2, which is less than 0. So here we have a negative second derivative. And on the right side, I'm going to just plug in 0. This is going to be 4, which is greater than 0. So this is positive. So this means that in this area, we're going to have concave down, and in this area, we're going to have concave up. So our inflection point is this. Concave up is going to be -2/3 to infinity. Concave down is going to be -infinity to -2/3. And that's our answer. All right, next question. Now, we have to find all the inflection points in the function, state all domains, same thing exactly as the last question. All right, f prime of x is going to be 6x plus 8, and f double prime of x is going to be 6. So as you can see here, if we set this equal to 0, that's never going to happen, which means we have no inflection points. So either the function is always concave up, or the function is always concave down. And since we have 6 here, that's positive, which means that the function is always concave up. So I'm just going to write concave up from -infinity to infinity. And this rule holds for all quadratic equations because their second derivative is always going to be a constant. No second derivative has an inflection point, so they're always either concave up or concave down. Okay, last question here. We have to calculate the inflection points and the concavity of sine of x between 0 and 2 pi. So first we're just going to find f prime of x is going to be cosine of x. And f double prime of x is going to be -0, pi, and I'm just going to put the end of our domain too. So in this area, between 0 and pi, let's just plug in some point. Let's plug in pi over 2. So f prime prime of, sorry, not x, pi over 2 is going to be just -1, which is less than 0. And for the section between pi and 2 pi, I'm going to plug in 3 pi over 2. And we're going to get +1, which is greater than 0. So I'm going to say that I'm actually going to cancel 0 as an inflection point because within our domain, an inflection point, we have to cross from negative to positive or positive to negative. But since there's nothing to the left of 0, we can't go from positive to negative or negative to positive. So 0 is not going to be an inflection point. Pi is our only inflection point. And so now we're going to just list our domains. We're concave up between pi and 2 pi. And we're concave down between 0 and pi. Alright, that was the last question for this video. I hope you found this helpful because I know it was a little bit longer and this is a very important topic as well. Anyway, I'll see you in the next video, and as always, keep learning.